Check. Okay. So today we are starting heat. Okay. Today we are starting heat, and there are some like messages to pass. I'll give all those information towards the middle of the class. But anyways, you have 2 sessions going on for 26 batch, 2 heat lessons. Today full English medium class from around 6:30 to 8:30. Okay, from around 6:30 to 8:30. And Sinhala and English class tomorrow, Thursdays, 9:15 to 11:15. Okay. Classes දෙකක් යනවා තාපයට full English medium එක අද 6:00 ඉඳන් 8:00 වගේ සිංහල and English එක හෙට බ්‍රහස්පතින්දා 9යි කාලේ 11යි කාලේ time slot එකේ. So did everyone get their tutes? Did everyone get their tutes? Yes. Physical class students. Online class students will provide the tute in the Zoom chat. Mali. Tute. Okay. Tutes are available in the Zoom chat, and sorry for any delays of the like to delivery of the tutes. Okay, as you know, there was the like a strike in the postal services. That's the issue. But now, like within few days, you will receive your tute, because anyways you can't print this because it's like 90 or 95 pages. The heat tute is huge. Okay, it's not actually a tute, it's a book. Okay, so like you will receive it maximum by next Tuesday, you will receive it. But if you like still didn't send a message to our coordinators requesting the tutes, okay, if you still didn't send a message to our coordinators requesting the tutes, please do send a message to this number. Okay, please do send a message to this number. Then they will deliver you the tutes. Tomorrow also we are sending a new batch of tutes, because we were actually waiting until the postal strike is over, because if we like hand it over to the postal services when the strike is happening, then we are in trouble, because I mean the tutes gets misplaced. Okay, they gets damaged. So we were waiting until the postal strike is over. So tomorrow also we are sending a new batch. So if you haven't still contacted our coordinators and requested for tutes, put a message to this number. Okay, 070-154-6825. Okay, so I'll start the lesson. Okay, I'll start the lesson. Heat or thermal physics. Heat. Molecules. Okay, thermal physics. Okay, so like I'll start with a very brief description about heat or temperature. Like what is heat or what is temperature? Quickly. What is heat or what is temperature? Let's start with that topic. What is heat or what is temperature? So basically, before moving into like complex content or anything like that, let's discuss about like what is this meaning of temperature or heat. First of all, we should have some kind of a meaning, like before writing any equations, okay, before understanding anything about equations, writing equations, doing calculations, defining proper definitions for temperature, before everything we should have some kind of a common sense about what is heat. Okay, we should have that kind of a common sense. So heat is actually like the particles, as you know, are vibrating always. Everything around is vibrating with a certain frequency. Okay, everything around this table, this TV, everything around is vibrating with a certain frequency, okay? The particles are vibrating, people are vibrating, the rays are going everywhere. This is a very complex system at all that we can't, that we can't actually understand. Okay, science can improve science can improve a lot. Still, we won't be able to understand some stuff properly, okay? So, the particles are always vibrating, and so particles are always vibrating like this. If you take a table, it's vibrating. If you take a bulb, particles of it is vibrating like this, okay? Now, when you touch this table, maybe, what happens? Assume like a hot object, okay, some kind of a object with a higher temperature. So higher temperature, what is this temperature? Temperature means basically this vibration of particles. Temperature and heat means basically this vibration of particles. Heat is a form of energy, okay? Heat is a form of energy. So what is this energy? Actually, heat is a form of kinetic energy, okay? Heat is a form of what? Form of kinetic energy. That means what we mention as heat is the kinetic energy of the particles that are vibrating, okay? Kinetic energy of the particles that are vibrating. Clear? Clear? That is heat. Then what is temperature? Temperature is the feeling that we get through that vibration of particles, how we understand it. That means when you touch this, the vibration of these particles starts colliding with the particles of your hand, which pass the vibrational kinetic energy to your hand. Clear? Which pass vibration of this, which pass that kinetic energy to the particles in your hand. Clear? Clear? Then what happens? Then that sensation you get through that, okay? That sensation you get through that is the temperature, okay? That is the temperature. So now your particles in your finger is vibrating, okay? Now you feel it as a temperature, okay? Now you feel it as a temperature. Clear? That's the story about, that's the story about temperature and heat. Mali. Next. So that is basically heat and temperature. Okay. So let's start with now proper physics, okay? Definitions and all. That is the formal or the common sense behind heat, okay? First of all, we should have a common sense about anything, right? So now whatever happens in heat, okay? Whatever happens in heat, attention, whatever happens in lesson heat, okay? Now you know the common sense behind it, okay? It's actually particles vibrating. If heat flows from here to there, what is the actual meaning of that? Vibration of these particles are moving towards that side. Clear? Like that, it's good to have this common sense. Okay. Next. Let's start with proper physics now. The zeroth law of thermodynamics. Zeroth law of thermodynamics. This is the first law of thermal physics. Actually, why do we call it zeroth law of thermodynamics without calling it the first law of thermodynamics? Because first law of thermodynamics was invented first. First law of thermodynamics was invented first, which we will learn a bit later. Then they understood that there's something more fundamental than the first law. Okay, then they have to give this name of zeroth law. Okay, so this is the zeroth law of thermodynamics. When I tell this zeroth law of thermodynamics, you will think that it is really absurd to have a law like this, but some definitions and some stuff in physics and maths are like that. Okay, because there's a huge story behind this. So what is zeroth law of thermodynamics? If A is in thermal equilibrium with B, B with C in a closed system, A and C also in thermal equilibrium. What is the meaning of that? Thermal equilibrium means actually equal temperature. So if A and B are in thermal equilibrium, that means A and B have the same temperature. And if B and C are in the same temperature, that means in thermal equilibrium, then A and should be in thermal equilibrium. Okay, then A and C should have the same temperature. So this is quite obvious, right? This is obvious, but like when you like properly define a subject, these kind of things plays a huge role which we still can't understand, because I mean in engineering also in the first semester we have to learn real analysis. I have explained this before. To prove that 1 plus 0 is 1, you have to write 3 pages of content. To prove that 1 plus 0 is 1. Yes, in your world 1 plus 0 is 1. But what is 1? What is 0? How the hell 1 plus 0 becomes 1? You have no answers, right? Clear? So when we dig deep into physics or maths, these kind of things plays a huge role. So in engineering, to prove that 1 plus 0 is 1, you have to write 3 pages of content sometimes. To prove that 0 into x is 0, you have to sometimes write 5 pages of content. Okay? Because I mean, how can you tell that 5 into 0 is 0? What is the logic behind that? And when it comes to vectors in our world, I mean in our physics, in our syllabus, like if it has a magnitude and it has a direction, it's a vector. It's simple like that. But in maths, proper maths, there are 10 vector axioms. Okay, there are physical quantities with a magnitude and a direction, but still fail 1 or 2 axioms are not, then they are not vectors. So there's a much fundamental layer of physics that we don't learn in our syllabus. These kind of definitions help in that. Okay, so you won't understand the need of this law without knowing that baseline of everything. Okay, okay. I mean it's like this. You can't just tell that if 1 plus 1 is equal to 2, you can't just tell this. You have to prove it, right? Like that, this thermal equilibrium, that means these two are in same temperature, these two are in same temperature, then these two are in same temperature. To prove that, they had to go through a lot of trouble, then they define this as a law. Okay, so you won't understand why do we have this law, but this is really important. Okay, this is zeroth law of thermodynamics. Okay, if B and A are in thermal equilibrium and B and C are in thermal equilibrium, then A and C are in thermal equilibrium. Clear? Okay. Then next one. Now I have defined temperature, physical quantity which decides whether two objects are in thermal equilibrium is temperature. See, then using the zeroth law, they defined temperature. They define temperature using the zeroth law. From my definition of common sense, temperature is the sensation you get through the vibration of particles. It's the common sense based definition. But the definition they have given is temperature is the physical quantity that we use to check whether two objects are in thermal equilibrium or not. What is thermal equilibrium? When I touch these two objects, whether these will pass kinetic energy to this. That is thermal equilibrium. When I touch these two objects, will this object pass kinetic energy to this? If they have the same kinetic energy, same vibrational kinetic energy, this guy will not pass kinetic energy to this guy, right? If the vibration of both particles are same, clear? Then we call that they are in same temperature. So temperature was defined on this Zeroth law. Okay, temperature is the physical quantity that checks whether two objects are in thermal equilibrium or not. Clear? Got the idea? Okay. Next. Now, how do we measure temperature? It's the next main requirement is that, right? How do we measure temperature? To measure temperature, we have different thermometric properties. Okay, to measure temperatures, we have different thermometric properties. What is thermometric properties? Temperature you can't directly measure, right? Length you can directly measure. Mass you can directly measure. Yes, you have the thermometer, but thermometer is not actually measuring the temperature, right? What you see is the expansion of mercury or a digital system, something like that. That means, yes, temperature is a fundamental physical quantity, I know that. But temperature doesn't show up itself like length. Length you can see, right? Clear? Length you can see. Mass you can see, right? Temperature you can't see. Why? It's vibration of particles. To see vibration of particles, you need a microscope. Okay? To see vibration of particles, you need a microscope. Okay? So temperature doesn't represent itself like length. Okay? Temperature doesn't represent itself like length. Okay? Then, if that is the case, we need some visual stuff to measure temperature. For that we use thermometric properties. Thermometric properties is physical quantities that changes with temperature. For an example, expansion of something. Take the mercury thermometer we use at home. In a mercury thermometer, what happens is, you have the thermometer, and when the temperature goes up, mercury expands through this, right? When temperature goes up, mercury expands through this. So this actually doesn't show the temperature. It shows the expansion due to temperature. Clear? This actually doesn't show the temperature. It shows the expansion due to temperature. Got the idea? What else? Pressure. Pressure of a gas increases with temperature. There's a lot of stuff. Digital thermometers, how do they measure temperature? In digital thermometers, they have a small resistor that changes its resistance with temperature. Clear? So it changes its resistance with temperature. So they measure the resistance and show the digital value as temperature. These are thermometric properties, things that changes with temperature. Clear? Clear? Next. So if we are choosing one thermometric property like this, okay, if we are choosing one thermometric property like this to measure temperature, okay, if we are choosing one thermometric property like this to measure temperature, it should have some fundamental qualities. Okay, it should have some fundamental qualities. They are, it should be a single valued function and it should be a continuous function for sure. That means, assume that you have a function like this, length or something. This is temperature. Let's assume this is resistance of a particle. So let's think that it changes like this with temperature. Now we are in trouble, right? Why? You measure the resistance like this. What is the problem? It can be two temperatures, right? It can be two temperatures. Clear? So you can't have functions like this. You should definitely have a single valued function like this. If you are using something to measure the temperature, it should be a single valued function like this. That means for one value you have one temperature. See? Clear? This is a must. So now we are in the process of creating a thermometer, okay? We are in the process of creating a thermometer. Okay, first of all we identify the required material, then we are going to create some thermometers, some units, okay? Next, it should be definitely continuous in the required region. That means, again R and theta, it goes like this, then a sudden jump like this, then a sudden jump like this. You can't have something like this, okay? This is not continuous. See, this breaks. So how can you create a function for this, right? Okay? If it breaks, if it doesn't have a proper function, you can't use that, right? Clear? Or else, if it loses a certain part, like this, you have a thermometric property, it shows values for this range, then nothing, then this range. Then again you are in trouble, right? Then again you are in trouble. Clear? So it should be continuous in the required range. Clear? These are the two fundamental characteristics. These two are must. Okay? These are must. And there's a set of characteristics that are not a must, but it's good to have these things. There are more characteristics. They are not a must, but it's good to have them. They are linear variation. Okay? If the variation of the thermometric property with theta is linear, it's easy to create an equation, it's easy to create an instrument, right? If it goes like this, still you can do, but it's a lot of trouble, right? To create an equation for this. Okay? This will be a complex equation, this will be a simple equation. Clear? So linear behavior is good, not a must. Okay? What else? High sensitivity, high range. These are good stuff. What is high sensitivity? Assume you have two materials. One is like this. And the other one is like this. Other one is like this. Here, it's really difficult to detect a small temperature difference. Why? For a small temperature difference, see, difference of R is really small. Here, for a small temperature difference of R is really small. Clear? For a temperature difference of R is very small. Clear? But here, for a certain temperature difference, you have a good change in R, good change in property. So it's detectable. It's easily detectable. Clear? You can easily detect this change. Clear? And it's good to have a good range. That means you have a property that follows all these rules in a very small range. Still you can create a thermometer using this property in this small range. There are some thermometers like that, okay? There are some thermometers that can measure from 0 Celsius to 5 Celsius only. But it's like extremely precise in that range. There are some thermometers like that. For specific use cases, they can measure from 0 to 5 Celsius only, but it's extremely precise. So still, from a, see, this have a very small range. You can, but it have all the properties. Clear? So you can use this to create a thermometer. Okay? You can use this to create a thermometer. Okay? But this is good. It has a huge range. You can detect a huge range of temperature. Okay? You can detect a huge range of temperature. Clear? Now, based on these characteristics, we are going to create some thermometers, okay? Based on these characteristics, we are going to create some thermometers. Now, what are the good properties of thermometers? Here we were choosing a characteristic, right? Whether it's expansion, whether it's pressure. Here we were trying to find the characteristic, proper characteristic. Now, what are the good characteristics of a good thermometer? First, we chose a property. Are we using the expansion? Are we using the resistance? Are we using the pressure to measure the temperature? Now, let's create a thermometer. What are the characteristics of a good thermometer? It should be easy to use. That's the main reason we are using the mercury thermometer. You place it somewhere and you look at that and you get the reading. Mercury thermometer is used. And that's the same reason that we don't use the mercury thermometer anymore and people use digital thermometers because it's easier to use. Digital thermometers are easier to use, right? Okay. I mean, I still can't see that mercury line in a mercury thermometer. I can't, I actually can't see that there. So still, that's why, due to the same reason, people use the digital thermometer. It's easy to use. What else? Readings are straightforward. Get the digital thermometer, reading is straightforward. Get the mercury thermometer, reading is straightforward. You directly read the temperature. But there are some thermometers, okay? You first put it into a certain temperature. It changes the resistance. Due to the change of resistance, it changes the current. Then you measure the current using the ammeter. Then using the ammeter reading, you measure the temperature. Okay? Sometimes we do this kind of stuff when we don't have a very expensive thermometer and we need to be really precise. Sometimes the mercury thermometer is not that precise, but we don't care. Okay? I mean, you don't have to measure up to nanocelsius, right? Okay, you don't need to measure the temperature of a person to nanocelsius, not required. Okay? But when we don't have the required instrument because it's really expensive, we create this kind of methods to measure the temperature, okay? We create this kind of methods to measure the temperature. Got the idea? So, these are not direct. Mercury thermometers are direct. And high sensitivity is good. Again, sensitivity means that thing. You have one mercury thermometer. When it goes from 1 Celsius to 2 Celsius, it changes like this. So you can barely see a change. But you have another thermometer, when it goes from 1 Celsius to 2 Celsius, its height changes like this. Okay? You can clearly see a change here, right? So it's easy to see a sensitive thermometer, okay? It's easy to read a sensitive thermometer. Sensitive thermometer means, sensitivity means per unit temperature, how much the change is. So when it goes from 1 Celsius to 2 Celsius, this will go like this. So you can clearly see, okay, the temperature has changed. But there may be some thermometers, when it goes from 1 Celsius to 2 Celsius, the mercury column goes up by 1 millimeter. 1 millimeter. Okay, you can't see that, right? Then, okay, see? So this is so sensitivity is also a good thing. What else? One of the important factors is the heat taken from the medium is minimum. What is that? There are some thermometers very small, so you need to measure assume this, you need to measure the temperature of a small droplet of water. You need to measure the temperature of a small droplet of water. For this, you use a very small thermometer. Clear? And in the next example, you use a huge thermometer. For the same droplet, you use a huge thermometer. What is the problem? Now definitely to assume that this is 40 Celsius. If this thermometer has to show 40 Celsius, first this thermometer should absorb heat from this droplet, and the mercury in the thermometer should absorb that heat, and the mercury should expand and show the value, right? So definitely some energy from this droplet is taken from the thermometer. But if the thermometer is really small, that amount will be small. Now when you use a huge thermometer, initially the temperature of the droplet is 40. Because the thermometer is huge, this thermometer will absorb a lot of heat before expanding. As a result, this will drop to 38. Now you are measuring 38. It's not correct, right? See, a thermometer, to show that temperature, it should first absorb heat. If that is too much, we are in trouble. Clear? So this is not a problem. This is not a problem when you are measuring the temperature of a huge beaker. Why? There's a lot of energy in a huge beaker. The amount taken by the thermometer, you can forget. Okay? Again, when you are measuring the temperature of a person, no big issue. There's a lot of heat in a person, so the amount absorbed by the person by the thermometer is negligible. But when you are measuring the temperature of something like this, a small droplet, now if the temperature is too high, it's a trouble, right? Now if the temperature is too high, it's a problem. Clear? That is the issue here. Next. Okay, next. Okay, so let's create a relationship. Okay, exercise 1, I mean, I had to teach this part before exercise 1, then it's easy to understand the exercise 1. How do we create a relationship? Okay, how do we create a relationship between thermometric properties and temperature? It's like this. I'll come to the definition of Celsius, Fahrenheit kind of stuff later. Okay, I'll briefly explain how do we create a relationship. Okay, I'll briefly explain how do we create a relationship between temperature and a thermometric property. It's quite straightforward when it is linear. Okay, it's really straightforward when it is linear. That means you can use this for anything. It's just the linear relationship that you have to use. That means when creating any thermometer, okay, when creating any thermometer or any when creating any thermometer or any unit related to temperature, what we usually do is we use two stable points. Okay, we use two stable points. That means think about, like, I'm giving you a rough idea now. Then when we start doing questions, you will understand this properly. First of all, let's think how do we create the Celsius scale. How do we create the Celsius scale? It's like this. We define two stable points. We define two stable points. That means we know that water freezes at an exact point. Under normal conditions, water freezes at an exact point, right? The freezing point, okay, or the melting point. We get that melting point and we call that 0 Celsius. We call that 0 Celsius. Then we know water boils at a certain temperature usually, right? Clear? We know that water boils at a certain temperature. So we get the boiling point. So we get the boiling point and call that 100 Celsius. That's how we create the unit initially. Clear? That's how we create this unit initially. Clear? We take the melting point and call that 0 Celsius. We take the boiling point and call that 100 Celsius. Now, anything in between now you can find, right? Okay? See, these are the two stable points. Clear? These are the two stable points used to create the unit called Celsius. See? So Celsius was created like this. Now you know Celsius. This is Celsius unit. This is Celsius unit system. Okay? This is Celsius unit system. Then Fahrenheit was developed in a similar manner. Fahrenheit is not actually is not mainly included in our syllabus, but it's good to know this because, I mean, although it's not in our syllabus, you know that, right? You know that there's a unit called Fahrenheit. So it's good to know this, okay? So again, when they were creating the unit called Fahrenheit, they took the melting point and called that 32 Fahrenheit. Clear? Then they took the boiling point. And called that 212 Fahrenheit. Okay? So actually, what was done in Celsius? They defined 1 Celsius as the difference in temperature, or this thermometric difference in between melting point and boiling point, and they divided it among 100 units. Then they called it Celsius. Clear? They took the difference, they took 2 points that they exactly know and which is easy to find in real life. I mean, now if you don't have a thermometer, still you can create the Celsius scale. Why? You take some water, you know that it starts freezing at 0. Okay? I mean, all these units on Earth are created in a way that they can face a extinction level event, but still we can create them. That's why previously 1 meter was a rod placed in SI headquarters. Now what is the problem? If someone steal that 1 meter rod, now we don't have a proper definition or a proper reference to 1 meter. Now people start violating what is 1 meter. Okay? So now 1 meter is not defined like that. They take light and they define it using light. That means the distance light travels in this much of seconds is 1 meter. Why? Now you only need the definition. Why? You go wherever you need in the universe, still you can create 1 meter, right? Now you don't have to take a 1 meter rod here and there when we are like, everything, although we don't know, we are doing in a way that we can go for the next level of civilization. Okay? In a way that things are expandable, things are recreatable. We should be able to face an extinction level event, but still we should preserve our science. Okay? Everything is defined in a way like that. Okay? We don't even think about this kind of stuff, but they think. Okay? They actually think. You know that. Like last year, not last year, the year before that, NASA tested first asteroid deflection mechanism, right? They sent a huge nuclear rocket kind of stuff and deflected the asteroid. Why? If a asteroid hits Earth with enough size, then we are in trouble. Nothing can stop that. Okay? But now we have some kind of a mechanism for that. Like that, although we don't even think about this, like the science is evolving in a way that those days the problems were like how things fall down, like those days the how to go from point A to B. Then they invented the wheel, then we invented the car, then we invented the train kind of stuff. But now the problems are not like that. Now we are planning on going to the next layer of civilization, which is really difficult. Okay, so here also, if we face an extinction level event, if you have nothing on paper, but still you can recreate Celsius, right? You take some water, you start boiling it. Okay? You call the boiling point 100 Celsius. You call the freezing point 0 Celsius. See, it's recreatable. See? So, any unit on planet Earth now refers to something that can be recreated. Okay? That's how things are defined now. So, Fahrenheit was made in a way that you take the temperature difference between the melting point and boiling point and divide it among 180 units. Okay? Then how do we connect these things? Okay, how do we connect these things with thermometric properties? That means, assume that you are creating a mercury thermometer. So what you do is you have mercury, you put it into freezing water. You know that freezing water is 0 Celsius. Now into this axis I put Celsius. You put your thermometer into freezing water. Then it will show a certain length. The mercury layer will show a certain length, like this. You measure that length. Maybe 2 centimeters, maybe 2 centimeters. Clear? Then you take this and put it into boiling water. Now you take this and put that into boiling water. Then it shows a length of 8 centimeters. So boiling water, you know, 100 Celsius, then it's 8 centimeters. Clear? Now you have a linear graph. Okay? Now what do? You take this gap 2 to 8 and divide it into 100 units and call it a thermometer that measures in Celsius. That's how we create a thermometer. Or else you put it into a certain liquid. If you have nothing written on this, it shows 6. It shows 6. Now what can you do? Since you have this graph, you write 6 here, and using the graph, you check the temperature. You can do that, right? Using this graph, you check the temperature. Clear? So what is actually the temperature at 6? 50, right? Looks like 50, right? How can I find that? Use the gradient. Gradient means if this is theta, gradient is 8 minus 2 over 100 minus 0. 8 minus 2 over 100 minus 0. This is the gradient. Clear? Then again you can write the gradient using this part only, right? Which is 8 minus 6 over 100 minus theta. 100 minus theta. Now you can find theta, right? Now you can find theta. You can solve this and find theta. Clear? Clear? That's how we connect some kind of a thermometric property to a temperature. So first we got physical properties and connected them to temperature scales. Then we took temperature scales and connected them with thermometric properties that we can measure. Now we have instruments that can measure temperature. See how things evolved? Okay. So it's like put a small note in your, like anywhere, like in your note or somewhere like that. I'll give a note next week, a small proper explanation about Celsius, Fahrenheit and Kelvin. Okay, I'll give you a proper note about that. Let's write a proper note and some stuff, additional stuff about that next week. Today I'm just building the common sense related to heat. So I'm not going to dig deep into definition of Celsius, dig deep into definition of Fahrenheit, dig deep into definition of Kelvin. We are not going to do that today. Today is just to build the common sense about the lesson. So we are not going to dig deep into that, but let's just write the general definition. What is Celsius scale? Just write down Celsius scale is created by dividing the temperature gap between the, just listen to what I'm telling and get the idea and you can write, okay? Celsius scale is created by dividing the temperature gap between the boiling point and the freezing point, or boiling point and the melting point, by 100. Okay, that's Celsius. Celsius scale is a scale that divides the temperature gap between the melting point and the boiling point into 100. Clear? Question? Okay, Celsius scale is created using Celsius scale is created by dividing the temperature gap between the melting point and the boiling point by 100. Clear? Melting point equals 0 Celsius, boiling point equals 100 Celsius. Just write these content. That's enough for today. To do the exercises related to today and to build the common sense, that is enough. But next week I'm going to do a separate lesson on these kind of things, because can you remember the fundamental unit of temperature? It's not Celsius, it's not Fahrenheit. What is that? Kelvin. So there's a lot of stories behind Kelvin, behind Celsius, behind Fahrenheit. That let's do next week. But to do the questions and to build the common sense, only the required amount I will teach today. Okay? Next week, let's go into the formal definition of Kelvin and all. So, again, I'll repeat. Celsius scale is created by dividing the temperature difference between the melting point and boiling point by 100. Melting point equals 0 Celsius. Boiling point equals 100 Celsius. Write that down for today. You don't have to worry much about that, because next week let's write some proper definitions for everything. Then Fahrenheit scale is created by dividing the temperature difference between the melting point and the boiling point by 180 units. Clear? Fahrenheit scale is created by dividing the temperature gap between the melting point and boiling point by 180 units. Clear? Then melting point is 32 Fahrenheit, boiling point is 212 Fahrenheit. Just having this idea would be enough for today's content. Melting point is 32 Fahrenheit, boiling point is 212 Fahrenheit. Melting point is 32 Fahrenheit, boiling point is 212 Fahrenheit. Clear, everyone? Clear? Fahrenheit scale is made by dividing the temperature difference between the melting point and boiling point by 180. Melting point is 32 Fahrenheit. Boiling point is 212 Fahrenheit. Clear? Then, usually when we are doing questions, we don't draw it like this, okay? These relationships we usually don't draw like this. There's no specific reason behind this, but maybe for convenience, attention, maybe for convenience we don't draw this graph like this. We usually write them like this in questions. Then when we write this, they know that this is the story. So this is the length, this is the temperature. At 0 Celsius, length is 2. At 8 Celsius, at 100 Celsius, length is 8. Now I need to find the temperature at 6. We usually don't draw graphs like this, we write things like this, okay? So again we do the same thing, okay? 8 minus 2 over 100 minus 0 equals 8 minus 6 over 100 minus theta. Same thing, okay? Same thing, but we usually don't draw the graph, we write it like this, okay? Clear? We write it like this. So, go to exercise 1. So you don't have to draw graphs. You can do things like this. Go to exercise 1 and do question 1, part A, 2 and 3. Sorry, 1 and 2. Part A, 1 and 2. Sorry, 1 and 5. Let's do 1 and 5 and part B. Then question 2. It will be available in the Zoom chat again. So exercise 1, question 1a, part 1. So now it's quite straightforward. 0 Celsius means in your thermometer 0 Celsius is shown as +2. So this thermometer we don't know. It may be the length 2, or it may be the temperature, it may be the resistance 2, it may be the pressure 2, something related to the thermometer. Then 100 Celsius is shown as 22. 100 Celsius is shown as 22. Clear? Then what is +7? What is +7? Clear? So use the gradient. 22 minus 2 over 100 minus 0. You actually don't need to get this minus this. If you like, you can go with this minus this, right? Clear? If you like, you can write 22 minus 2 equals 100 minus 0 equals 22 minus 7 over 100 minus theta. Or you can write 7 minus 2 over theta minus 0. This also works, right? 22 minus 2 over 100 minus 0 equals 22 minus 7 over 100 minus theta, or 7 minus 2 over theta minus 0. Clear? So what is the value of theta after solving this? You would get 20 5 into 100 over 20. So you are getting 25. Theta equals 25 Celsius. Theta equals 25 Celsius. Then part 5. Again, 2 means 0 Celsius. 22 means 100 Celsius. Then what is 30? So 30 is not here actually. What is 30? What is 30? But same thing, right? Same thing you have to do. 22 minus 2 over 100 minus 0 equals, you can write anything, equals 300 minus 22 over theta minus 100, or 300 minus 2 over theta minus 0. Clear? Why both works? This is a linear graph, right? This is a linear graph. Theta and something. 2 means 0. 22 means 100. Then 300 means, 30, right? It was 30, right? You had 30, right? Yeah. 30. What is theta? So this is just a graph. So write equations for gradient, okay? So if you like, you can write 22 minus 2 over 100 minus 0 equals, if you like, you can write for this point and this point, or this point and this point, right? If I choose this point and this point, it's 30 minus 2. It's 30 minus 2 over theta minus 0. Theta minus 0. Clear? Then what do you get by solving this? 28 into 100 over 20. You get 140. Theta equals 140 Celsius. Then part B, what is the value corresponding to 80 Celsius? Before answering that, okay, before answering that, I would answer the next part of that question. Express, attention, express your idea about the accuracy of the answers you obtained in 5 and 6 parts in A above. So it's not that accurate, right? We don't know for sure. That is the only problem. We don't know for sure. That should be the answer. Why? When I was creating this thermometer, okay, when I was creating this thermometer, I used 0 and 100. Then I predicted the pattern. Clear? But this is 140 Celsius. I'm talking about the answer for fifth one. For the fifth one, answer is 140 Celsius. For this to happen, this linear graph should continue up to 140, right? For me, this to happen, definitely, this linear graph should continue until 140. But I don't know that for sure. I stopped the practical at 100 Celsius. So who knows whether after this point, whether it goes like this? We don't know, right? I checked my thermometer from 0 to 100 only. I used 0 and 100 to calibrate my thermometer. Okay? But who knows what happens after 100 in my thermometer? Assume in your thermometer you have water. After 100, as your thermometer, you use the expansion of water. After 100, water vaporizes, right? So you assuming that you can measure after 100 is wrong. If your thermometer is not mercury thermometer, if it is a water thermometer, you do the practical from 0 to 100 and you get the height of water column, and you think that you can use that thermometer to measure 140, it's entirely wrong. You don't have water at 140, right? See? So when you do a practical from 0 to 100 and test, after that what's going to happen, you actually don't know. So there's an accuracy issue. Then you may think, then what about all other thermometers? No. Industrial thermometers, they check for higher temperatures. Although they use 0 and 100 to write the scale, in the box of the thermometer they write this can be used from minus 20 to maybe 250. They check the thermometer to from minus 20 to 250, okay? So in the industrial thermometers, they don't have an issue like that. But when we create our own thermometer and we check it from 0 to 100 only, we don't know what happens after 100, okay? So that is the answer. We can't, like, this accuracy of the thermometer is not confirmed because we don't know the behavior of the thermometric property after 100 Celsius. This is a complete answer, okay? The accuracy of the temperature is not confirmed because we don't know the behavior of the thermometric property after 100 Celsius. Clear? Clear? Because we haven't tested it. Okay, we haven't tested it. At the same time, I'll get the answer for part B too. In the part B, they are telling what is the thermometric property, what is the value at 80. So now it's the other way around. So it's 2 at 0 Celsius, it's 22 at 100 Celsius, then what is the value? I'll take it as L at 80 Celsius. What is the value at 80 Celsius? So 22 minus 2 over 100 minus 0 equals L minus 2 over 80 minus 0. What is the thermometric property shown now? It's 18. It's 18. Clear? The value is 18. Next, question 2. Let's go to question 2. Then others, you can keep doing the questions 3, 4, 5, 6. Continue the exercise. Okay. Today we are just getting familiar with these kind of concepts, these kind of calculations, because there's a lot of applications of this kind of stuff in questions. A faulty thermometer reads 1 Celsius for the freezing point of water and 105 Celsius for the boiling point. In this thermometer, if the temperature is 52, what is the corresponding temperature? If the measurement is 52. So there's a faulty thermometer. Okay, write this down if you're writing anything. Okay, so a faulty thermometer shows 1 Celsius for the freezing point and 105 Celsius for the boiling point. In this thermometer, if the measurement is 52 Celsius, what is the correct corresponding temperature? What is the temperature shown by the thermometer for a temperature of 60 Celsius on a day where the room temperature is 30? What is the temperature shown by the thermometer? I'll do part 1 and 2 only. I'll do part 1 and 2 only. Question 2. Again, there's a faulty thermometer. This is the actual temperature, this is the shown temperature or the reading. I'll write this as reading and this as the actual temperature or theta. Actual temperature or theta, this is the reading. We know that the freezing point is actually 0 Celsius, but due to some kind of a fault, my thermometer reads it as 1. And we know that boiling point is usually 100, but due to the fault, it reads the boiling point as 105. Now, if the measurement is 52, that means if the reading is 52. Question? Yeah. Sorry? Yeah. No, like in this area, we consider both melting point and freezing point as same. That means freezing point is the temperature, it starts freezing. The melting point is the temperature that ice starts melting. So both we consider as 0. Okay, water turns into ice at 0, ice turns into water at 0. That's why I took freezing point as 0. Okay, that's the reason. So in our syllabus we don't have two separate definitions for that, but I know that there's a different science behind like freezing and melting. But in our syllabus, if they mention freezing point or melting point, for both we consider it as 0. Okay, in our syllabus we consider both freezing point and melting point as 0. So if the reading is 52, what is the temperature? So what can I do? Same story, 105 minus 1 over 105 minus 1 over 100 minus 0 equals 52 minus 1 over theta minus 0. 105 minus 1 over 100 minus 0 equals 52 minus 1 over theta minus 0. Using this you can find theta. Then this is 1. What is the temperature shown by the thermometer for a temperature of 60? So you can solve this and find theta. Then again in the second part, reading and theta, 1, 0, 105, 100. If the temperature is actual temperature is 60, if the actual temperature is 60, what is the reading of the thermometer? So 105 minus 1 over 100 minus 0, this gap over this gap equals this over this, r minus 1 over 60 minus 0. You can solve this and find r. Go to question 3. Go to question 3. I'll calculate these two. Here theta is 49. Theta is 49 Celsius. That one. Reading is 63.4. Reading is 63.4. Go to question 3. Create a relationship between Celsius and Fahrenheit. And try question 4 too. I mean, question 4 and 3, you can use the same thing, right? Just continue. Try to finish the exercise. Obtain the relationship between Celsius and Fahrenheit temperature scales. Obtain the relationship between Celsius and Fahrenheit temperature scales. So you put Celsius in one side, Fahrenheit in this side. So melting point is 0 Celsius. What is the Fahrenheit value? 32, right? Fahrenheit value is 32. Boiling point Celsius 100, Fahrenheit 212. 212. So just like another relationship, right? Then if a certain temperature is in theta Celsius, this is the Celsius value. If this is the Fahrenheit value, now we can create the relationship, right? Clear? For a given temperature, this is the Celsius value. This is the Fahrenheit value. Clear? So what do you get? 100 minus 0. 100 minus 0 over 212 over 32 over 212 minus 32 equals theta c minus 0, theta c minus 0 over theta f minus 32, theta f minus 32. Clear? Clear? Now what do you get? Here 100, here I think 180, here theta Celsius, here theta f minus 32. So theta f minus 32 equals, theta f minus 32 equals 1.8 theta c. I took them here, then theta Fahrenheit equals 1.8 theta Celsius plus 32. This is the relationship between the Fahrenheit scale and Celsius scale. Clear? Using this equation, if they give the temperature in Celsius, you can get the answer in Fahrenheit. If they give the temperature in Fahrenheit, you can get the answer in Celsius. Clear? Clear? Got the idea? Just the linear relationship between these two. Clear? Question? So in a question, if they mention lower fixed point and upper fixed point, if they are not mentioning the lower fixed point and upper fixed point, it's definitely 0 Celsius and 100 Celsius. Okay. So as a standard, if they are not giving the lower fixed point and the upper fixed point, we definitely get 0 and 100. Okay. The melting point and the boiling point. 1.8 theta Celsius plus 32. Then in question 4, is this clear everyone? This one? Yeah? Clear? The relationship between the Celsius scale and the Fahrenheit scale. So this is one of the lengthiest lessons in the syllabus. Okay, I mean, mechanics is lengthy, but there's not much theory, right? It's just a bunch of questions. Mechanics takes time because we have to do a lot of questions. Heat is not like this. It's the same size as mechanics, but theory. Okay, it has like 2 times more theory like mechanics. A huge lesson. Like later we can decide whether we are choosing this question or not. Okay, that heat part is one of the main areas. I mean, if you take the timeline of physics, how things happen is like at the beginning people give up because mechanics become difficult. Okay, at the beginning people tend to give up, but then later I didn't understand that there's no way out. You have started anyways doing science, so somehow pick up mechanics. Okay, so barely manage stuff in waves and optics. Then again comes heat, another main war zone. People start hating physics in the lesson heat because it's huge. Okay, it's huge. But if you survive heat, okay, if you survive heat, then after that the syllabus seems easy because again the interesting parts like electromagnetics kind of stuff appears. Small lessons after that. After that all the lessons are pretty small. The problem with these large lessons, it's not because the lesson is large, because you have to remember things for a very long time, and since you never revise things again, okay, larger the lesson, the more content you forget about the same lesson, so the less you understand in the same lesson. That's why people usually hate huge lessons. Why? You never revise things. Okay, so if the lesson spans for like 6 months, you will anyways forget first 2 months of content. Then later when we refer to that, you have no idea, then you are in trouble, then you think the lesson is difficult. Same old story. Okay, same old story. But in small lessons, no big issue, you never revise, but still since the lesson is small, you can remember the initial content, so you can understand up to the end, and luckily it finishes on time. So that is the problem with these huge lessons. That's why people drops out of physics. That means people like start ruining physics, getting low marks for physics, like in these 2 lessons mainly, mechanics and heat. Because the only reason is people never revise content, never revise last week content, never revise last month's content. Okay, so it's better to have a plan. Okay, it's better to have a plan in the sense, before this class, keep a dedicated half an hour or 1 hour that you would use to revise this content. Okay, don't allocate anything on that time, anything for that time. That means if this is Wednesday, maybe Tuesday night 9 to 11, okay, or 9 to 10 at least. Make sure that that time is allocated. It's a part of the class. Okay, it's a part of the class. Whatever happens, whatever the homework you have left to do in other classes, whatever the term test coming, okay, whatever the event you have, no matter what is happening, you use that time to revise. Okay, for sure. Then keep a day to revise last month's content. That means maybe 27th of every month, or somewhere between 26, 27, 28, you take 1 full day and revise last month's content. So if it is, I mean, why did I mention 3 days? You can't skip a day you have classes, right? You can't skip a class and stay at home and revise content. But maybe on assume like 26th is a Friday, you don't have classes. Maybe take a holiday from school too. get one full day and revise last month's content again. Okay, if you can do this thing, all these subjects are really easy if you did this from beginning, okay? Because I mean, the only thing that these island first people tell is, Mama edinada wada edinada kara. Okay? Okay, what they usually tell is they did whatever they had to do on the same day. And I mean, I'm in University of Moroto, so we anyways meet all the island first people, right? And I'm in the electronics department. Electronics department means anyways like 90% of the island first people are in the electronics department. So we daily meet like all the island first people, district first people. The nature of all these people are they don't work a lot. They are not really smart. Okay, they are not really smart. They don't work a lot. But I mean, it's a headache for them if there's anything left to do. Like if something's off their plan, it's a headache for them. That's the nature of these island first people. That means if they don't revise yesterday's content, it's a headache. So they somehow manage half an hour and revise the content. And the best thing is, this method consumes the lowest amount of time to study. Why? Studying last week's content would take 15 minutes because you can remember stuff. If you go home today and tomorrow if you revise this content, it's really easy. It would take only 15 minutes to study this. So if you go home today and tomorrow if you study this, it would take 15 minutes. Next week before the class to revise this, since you studied twice in the class and tomorrow, you will anyways remember, it would take 20 minutes. So to revise everything, it takes around half an hour only. You just ignore everything and you start studying after 2 months. To study the same amount of content would take 2 hours, right? Why now you can't remember what I said. So now you have to understand everything by yourself. See? So this model that these island first people work, it's the easiest method that you can work the minimum amount of time. Okay? I mean, all these like high-ranking people, they watch a lot of TV series. Okay, usually they are lazy. Okay, I mean, I'm not an island first guy, but I was for 4 semesters I was the batch top at University of Moroto, but I'm not the island first guy. Okay. So these island first people are usually lazy. They don't work a lot. They just do the bare minimum, but they just do it on the right time. They study yesterday's content today, not next month. So they are really, really lazy. So they quickly finish stuff. For me, why I get a lot of marks in the university? Because I'm really accurate. Not because I'm intelligent, I'm really accurate. I have developed a level of accuracy that I don't make mistakes in a paper. That means if I know 50% of the content of the paper, I would get 50 out of 100 for sure. I don't make careless mistakes in papers. I have improved my discipline up to that extent, and at the same time, doing classes helps a lot in that. Why you have to keep a lot of attention, whatever the thing going on, whether you are having fever, whatever the issue you have, whatever the problem you have at home, whatever the problem you have in your company, whatever the problem, whether you have exams tomorrow or not, whatever happens, I have to keep my mentality, keep things stable and teach properly. So teaching helped me a lot in keeping attention. It helped me in the exam. So I'm usually really good at exams. Okay. If I write something, it's correct. If I don't, I don't go for lectures. Okay. For the last 6 months of my university, I went only 2 days to the university. Okay. For the last 6 months of the university. For the last year, maybe 10 days. Okay. What I do is when it is close to exams, I gather all the notes from the best people. Okay. Then I call some seniors, ask them how to study for this module. Then they give us a set of guidelines. Okay, Malli, this is how they give the paper. I study only that part. Okay, I study only the required part because I don't have enough time. I have to do classes. I have to run my company. So I study only the required parts. Then for sure, because of the attention and the discipline I gained by doing classes, the content, small content that I know, I can write it in the paper with 100% accuracy. That's how I got marks in the university. Okay, so things that we don't think help us in our exams. Okay, so like this keeping your attention kind of stuff are really important. Okay, so like that's why you usually don't get marks if you are using a mobile phone here and there. Okay, if you can place your mobile phone out of your room whenever you are studying, would improve your marks a lot. Not because you are studying a lot, because now when you don't have your mobile phone close, your attention span improves. Now you are much accurate. Like that, very small things that we don't think, it helps us a lot in exams. Okay, it helps us a lot in exams. For an example, me doing classes have nothing to do with exams, but at the end of the day it has everything to do with exams. So small things that we don't care helps us a lot in exams. But the basic idea is these island first people, they are the laziest people that I have seen, but they do the right thing at the right time. It's a headache for them if they keep something to study for the next week. Why? They know that pain, because they can't remember a thing after 1 week. So yesterday's content they study today. They know that pain. Okay, so as a result of doing it for a very long period of time, now they hate keeping something for a week, because they know that it's a headache. They need to study quickly and finish their TV series. These are the kind of people who finish a TV series in 2 days. Okay, like insane. Okay, many island first people actually. I don't know whether you believe this or not. These are the kind of people who would finish a whole TV series in 2 days. Why? Yesterday's lecture content, today's lecture content, lecture stops at 8. He goes home, at 9 he starts studying, then 9 to 11 he stops studying, everything is done. Then from 11 to maybe tomorrow they have lectures at 3, until 1 they watch their TV series, sleep for 2 hours, come to the lecture. These are the kind of people. So they know that if they keep this for 1 week additionally, okay, if they are going to study these in the next week, it's a huge headache for them. Okay, so they know that pain. Okay, now the problem is the best people are the laziest people. Now the laziest people, after 1 month, they are the people who works really hard. Why? They didn't do the correct thing at the correct time. So it's timing. Okay, it's not the amount of work or the length of work you are spending. Okay, it's you studying the proper thing at the proper time. Okay, some students, you learn physics, but these days your chemistry is not good, so you study chemistry for the whole month. Now the next month your physics is not good. Instead, what you can do is, you go home today, spend additional half an hour, study physics, done. Then tomorrow let's study chemistry. A very small change in your plans, okay, can bring a huge change. Okay, so keep that in mind. Okay, so next. So using the same equation, at a certain temperature, this is the relationship between theta Fahrenheit and theta Celsius. Theta Fahrenheit and theta Celsius. Now, the value shown in the Fahrenheit and Celsius scale takes the same value for one temperature. What is that? Okay, there's a certain temperature, it shows same value for both Celsius and Fahrenheit. That means in the Fahrenheit scale it shows as K, in the Celsius scale it shows as K. What is the value? Just solve this. In the Fahrenheit scale it's K, in the Celsius scale it's K. Clear? Now find K. Okay, find K. What is the value? 32. Is it minus? Did I get anything wrong, or it's actually minus, right? The actual answer is minus then. So 32 minus 32 over 1 minus 1.8, which gives you minus 40. Minus 40. K equals minus 40. See, at minus 40, You look at a Celsius scale, you see minus 40. You look at a Celsius scale and a Fahrenheit scale both, you see minus 40. Clear? So this ice point, like melting point, freezing point, all these terms refers to the same thing. It's 0 Celsius, okay? Yeah. I'll go to question 7. There's a temperature scale. It shows minus 20H. It shows minus 20H at lower fixed point. Lower fixed point means 0 Celsius. It shows minus 140H, at upper fixed point, which is 100 Celsius. What is, okay, it should go in this direction. I mean, but no matter how you write this, you are going to get the correct answer, okay? You don't have to think, okay, I should write this up or what. You don't have to think, just write, okay? Minus 20H, minus 140H. Then, what is the value shown for 30 Celsius? I'll take it as K. Clear? What is the value shown for 30 Celsius? I'll take it as K. So, this minus this over this minus this. Minus 140H minus 20H divided by 100 minus 0. Minus 140H minus 20H divided by 100 minus 0 equals K minus 20H, K minus 20H over 30 minus 0. K minus 20H over 30 minus 0. Clear? This minus this over this minus this equals this minus this over this minus this. So, minus 120H over 100 equals K plus 20H over 30. K equals minus 56H, minus 56H. Clear? Minus 56H. What is the value of 100H? What is the value shown in H scale for temperature 343 Kelvin? Kelvin, let's discuss next week. So, did you understand everything up to this point? I need to mention one small thing. What I need you to do is, Like you have to read next 2 pages by next week. You have some definitions of different thermometers. You have mercury glass thermometer, glass alcohol thermometer, thermoelectric thermometer. There are advantages and disadvantages. Read that part, okay? So for an example, if we take mercury glass thermometer, okay? If we take mercury glass thermometer, what is the thermometric property used? Expansion of mercury. What is the thermometric property used? Expansion of mercury. So what happens? You put mercury and it expands. Its range is written in Kelvin. So what is the usual range of a mercury thermometer? When you keep decreasing the temperature, at a certain temperature, mercury will turn into a solid, right? And when you keep increasing the temperature, at a certain temperature, mercury will vaporize. Between this, you can use mercury as a liquid, right? So that should be the range, but that's not the actual range. Why? There's a certain range that mercury expands linearly. After a certain point, it's unpredictable. And again, up to a certain point, this will behave linearly. After that, this is not predictable. So there's a limited range that mercury would behave linearly as a proper thermometric property. In that region, we can use mercury. Okay. The best thing is mercury, as you know, is a metal. So you can increase its temperature to very high values. Okay. You can increase its temperature to very high values. It will not vaporize like water. Okay. So you can measure this up to huge temperatures. Actually, before mercury vaporizes, the glass will melt. Okay. Usually we use glass for mercury thermometers. Before mercury vaporizes, the glass will melt. So mercury is a very nice, a very good option to measure high temperature values. And at the same time, since it is a metal, it's a conductor. Since it's a metal, it's a conductor. So mercury responds very fast. That means when you put this into a certain temperature, this should absorb heat quickly and expand, right? This should absorb heat quickly and expand. Mercury do this really fast. Why? It's a conductor. Since it is a conductor, mercury absorbs heat really fast and expands, okay? So it responds better, okay? So it has a very good sensitivity. Its length changes a lot. It reacts fast, okay? Mercury reacts fast. And it has a wide range, around -39 Celsius to 357 Celsius. It has a wide range, okay? And one good property of mercury, it's opaque. It's not transparent. You put water into a tube like this, you can't see the water column. But you put mercury, it's opaque, so you can see the mercury column going up. So as a result, mercury thermometers are easy to use. Okay? Mercury thermometers are easy to use. You can directly get the reading. Using the mercury thermometer, you can directly get the reading. Then it changes quickly. So to measure temperatures that change quickly, you can use this. Because mercury is a conductor, it absorbs heat fast and show the change quickly. So to measure temperatures that change quickly, you can use this. Then, yeah, so these are the main advantages. The disadvantages, it's not that linear sometimes. The behavior is not that linear sometimes. It doesn't expand linearly always. Then, to bulb mercury, not only mercury, bulb expands. When the temperature goes up, not only the mercury, this glass and bulb expands, which may create some errors. Okay, which may create some errors. Then definitely it absorbs a certain amount of heat to expand. Clear? It absorbs a certain amount of heat from the medium before expanding. Clear? It absorbs heat, which decreases the accuracy, right? Because if it absorbs heat, it will decrease the temperature of the medium that it measures. So it absorbs some heat. And you can't measure below minus 39 Celsius. You can't go below minus 39 Celsius. Clear? So like this is just a theory part, okay? Nothing to teach in this area. So I need you to read these 2 pages and try exercise 2, okay? At home, read these 2 pages, understand the properties of these thermometers, what are the benefits, what are the issues of these thermometers, and try to do exercise 2. Next week I'll teach these parts and explain about the Kelvin scale and all. Explain about the Kelvin scale and all. Then teach. Then let's move to expansion and other content. Thank you.